welcome back to my class. So, just before going further into whatever I'm going to discuss today, so let me come back to the problem that we were considering yesterday, and maybe I was not able to explain how the tensions, I mean T1 and T2, if you sum them up, you get the weight. So now today I have the problem. So this is exactly the situation. This is exactly the situation. You can see that this is the weight. This you can consider to be W, and then you can see that the weight is being held by this string in such a way that there is some kind of going to be some upward pull along this direction and along this direction. Is it okay? And you can see that these two upward pulls, that is nothing but the tension, it is balancing the weight downwards. Okay. I hope now the concept of how the sum of tensions T1 and T2 is equal to the weight W. I hope it is clear, right? Okay, fine. So then again, let me come back to the direction cosine. I just want to say a few things about that direction cosine. So if you recall, the direction cosines were nothing but with respect to a vector, with respect to a vector OP, with respect to a vector OP, where I was assuming the coordinates of P to be equal to A1, A2, and A3. And then what we did, we simply considered, I mean, the three standard basis vector along x, y, and z axis. Okay, and then we had seen that your cos alpha, it turned out to be A1 by A bar, and cos beta, you know, alpha beta are nothing but the angles made by this vector, which x-axis, y-axis, and z-axis. Okay, and cos beta was equal to this, and cos gamma, this is equal to this. Okay, and from here, I can see and that means if you consider the vector A was simply what? A was simply your A1i plus A2j plus A3k, right? And from these three, what I get? The values of A1, A2, and A3, right? And from here, I can write that this is simply your this is simply your cos alpha I plus cos beta j plus cos gamma k. Is it okay? Fine?
Yes. Yes.
Thank you. So so in this way also, the vector A can be expressed. So I'm going to come back to these three again later on today, when I'm going to do the vector equation of a straight line. I see something more on this. Oh, fine. So now, from here, further, what we can do from here, you are going to find out that vector A by the magnitude of the vector A, this is simply the vector with component cos alpha, cos beta, and cos gamma, right? Now, if you look at this expression, what this expression is, this is a spatial vector. It is a unit vector because I am simply dividing A by its magnitude, right? So this is a unit vector. So that means your cos alpha cos theta, cos gamma, which are nothing but the direction cosines of the vector OP, they are nothing but the components of a unit. Okay, fine. So now I'm going to move to a very important concept. I mean, this concept, you are going to apply it in your engineering part quite frequently later. Uh, okay, just fine. So now I'm going to discuss about projections. Okay. So whenever we talk about projection, in fact, we have to talk about both scalar and vector projections. And you will see that it's pretty straightforward. Okay. Suppose I am considering two vectors, your A and B. Okay, fine. And suppose the angle between them is, say, theta. Okay, so then if you draw a perpendicular from the final point of the vector B to the vector A, to the vector A, to the vector A, fine. So then this particular length, okay, say if I say suppose this is O, suppose this is P, this is say Q, the target point of this is Q, and suppose this is L. Okay, so then I can consider this particular length to be such that it is going to have the shadow. It is going to have the shadow of this vector B over the vector A. Okay, so now if I consider the vector OL, it is called the vector projection. Of the vector B over the vector A. Okay, and if you consider the magnitude of this, OL, then it is called the scalar projection of the vector B over the vector A. Okay, and they have got specific name for it. I think one is called cross, one is called comp. Okay, so this one, vector projection, it is denoted by this symbol, projection of the vector B over A. And because this is simply component of it, so that is why this one is called component of the vector B over A. Okay, just let me put my dividing side of this. Okay, so now the question is how we are going to express those vector projection and scalar projection in terms of the original vectors A and B. Okay, fine. And here the concept of unit vector is going to come in handy. Okay, now suppose I consider a unit vector A cap, along the vector A, right? So then you know that this one is simply given by this. Okay, fine. We are going to make use of this later. So now, if I consider this OL, this mod of OL, so this is nothing but mod of B cos theta. Is it okay?
Yes.
Fine. So that is why I can again write it as your cos theta by this. Okay. And what is the numerator here?
Dot
The
product.
dot product.
This is simply the dot product of A and B. Dot product of A and B. Right? So now you have got the formula for component of B over A. So this is simply A dot B. This. Fine. So
Yes.
now let us come to the vector projection. You know that vector projection is nothing but this vector OL. And yesterday I told you how do I get OL? OL is nothing but what? Any vector, what? How can you get it? You simply multiply. Say from here, while A is simply magnitude of A into a unit vector along that, right? So that means OL. This is simply magnitude of OL and a unit vector along OL. And a unit vector along OL is nothing but a unit vector along OQ or A, right? And that is simply nothing but this. Is it okay?
Yes.
Yes, sir.
Yes. Fine. And from here, I have already found out that OL is simply your what? Your
A dot
yes.
B
A dot B mod of
upon mod A.
yes. So I'm thinking whether even without using yeah, fine. So it is A dot B mod of A and then A this and this can be written as simply A dot B A divided by A square. So remember this part within that curly bracket, it defines a scalar. It defines a scalar. So basically, the scalar into a vector is a vector. Okay. Whereas this is entirely a scalar because A dot B, you know, dot product is a scalar. This is also a scalar in the magnitude. Okay. So eventually, this is a scalar. So that means form of B over A is a scalar, but projection of B over A is a vector. Okay. So that means this is nothing but projection of B over that's is it clear? Right? So now another thing I want to emphasize here. Okay. Here it was pretty well said that the angle theta that was an acute angle, right? So what happens if the angle is obtuse? Okay, I mean exactly which length are you going to consider in order to find out the vector projection and scalar projection? This is very straightforward. So what you have to do, so my situation is, if my situation is something like this, my situation is something like this. Sorry, let me use different colors so that this is easier for you to differentiate. Okay, say suppose I have this situation. Say this is A, okay, and this is a B, okay. Fine. So, and this angle you can see that definitely it is factor. So, what you have to do then? See, always remember, I am going to take a perpendicular from the terminal point of vector B. So, it is going to be something like this. And then I am going to extend this in such a way that I now what I'm going to do, I'm going to take, say, this is A, this is Q, and L. Okay, so this is the way I'm going to do. So that means your this length, this length, this length I will consider for my scalar and vector projection. Is it okay? Fine. Okay. So now let me just show you one application of this. Okay. Suppose you are applying some force. So suppose you are trying to drag something. You are trying to drag something from the point P along the horizontal direction with a force say F in this direction, and P is moved to the point Q. Fine. So then this PQ is nothing but my displacement vector. Displacement vector. Okay, fine. So then what is going to happen? So then you know that the work done, which I am going to denote by this, work done, W by the force F in moving is a particle say from P to Q. What it is? Do you recall?
Distance.
Do you recall it? See, now let me come to the point. Okay. So now, as I have told you, the point P was lying on the floor. So basically, point P was along the horizon, right? So that means the dragging something from P to Q, which was happening along the floor, that is being accomplished by the component of the force F along the horizontal direction, isn't it? And as before, as we did earlier, that is nothing but
Mod of
F cos theta, mod F cos theta, right? Okay. So the component of that force into displacement. Displacement is nothing but mod of PQ, isn't it?
Yes.
Fine. So if the displacement vector, if I call this simply as the vector D, okay. So then this force is going to be given by F cos theta, and what this is what this, okay, fine, and this is nothing but what
The dot product.
Dot product of
of F and T. That's it. Is it okay? Fine.
Yes.
And although this is not a direct application of the projection, but these also eventually, if you want, you can think about expressing it in terms of projection. Okay, fine. So this is about projection, and I'm happy that this resolving a vector into two components into the that is coming in handy today. Okay. So now, okay. So now let us come to a very important concept. Vector pair. what I'm going to do, I'm going to consider the vector product of vectors A and B. Okay. Now, let me again go back to your scalar product or dot product. So if you recall, if we consider two vectors A and B, right? And I know that they are orthogonal if and only if their dot product is C. Is it okay? This will be yes.
Yes, sir.
Now, suppose my A is given by this A1, A2, A3, and B is given by say B1, B2, and B3. Okay. Now, suppose I am seeking a vector C in such a way that C is perpendicular to both A and B. Fine. So then what must happen? What must happen? I must have A dot C equal to 0. And if I assume that the components of C are C1, C2, C3, I'm going to get this, and I'm going to get B dot C also is equal to 0. And remember, these two relations, they have come from the assumption that we are seeking a third vector C in such a way that both A and B are perpendicular to the same vector C. Okay, fine. So from these two relations, what do we get? We get A1 C1 plus A2 C2 plus A3 C3, this is equal to 0. And then B1 C1 plus B2 C2 plus B3 C3 is equal to 0. Right? So far so good. Up to this it is all right. Right? So suppose now I want to solve, of course, I try to find out C1, C2, and C3. But because we have what? We have, only two equations in three unknowns, we cannot uniquely solve it. Okay? Because you guys are going to do linear algebra only in your second semester. So that is why I'm not going to use any, linear algebra concept here. Let us try to do it in some other way. Say, suppose I am trying to solve, say, from these two equations, what I am going to do, A1 C1 plus A2 C2 equal to minus A3 C3, and then your B1 C1 plus B2 C2 equal to minus B3 C3. Say, suppose I am trying to solve these equations for only C1 and C2. Fine. So then what we can do? We can simply use Cramer's rule. Definitely you guys are familiar with Cramer's rule. Okay. So let us try to do that. So now, again, let me try to recall what was there in Cramer's rule. If you recall, like suppose I have something like A1 X1. Simply let me call y, A2y equal to say P P1x plus D2y equal to say Q, right? So if you recall, so then what we have, I have this relation. I have A1, A2, B1, B2, okay, y. Then I have this relation. I have this relation. Okay. I had x equal to A1, A2, B1, B2, and what I'm going to do here, simply A1, B1, I'm going to replace it by P by Q, then this is A2, B2, fine. So similarly, your y is going to be A1, A2, B1, B2, and again, I am going to replace here this column by P and Q. Right? That is what Cramer's rule was. Okay? So now, if I adopt the same methodology here, in order to find out your C1 and C2 from these two equations, so then what is going to happen? Your C1 So this is simply A1, A2, B1, B2, and then here A2, B2, and simply minus A3, C3 minus B3, C3, right? And then your C2 is again you're going to be A1, A2, B1, B2, and again now this is going to be A1, A2, and here I'm going to replace it by A3, C3 minus B3, C3. Okay, fine. And from here, what I can get eventually, if you do operate at, you are familiar with determinants, definitely, right? So these are nothing but determinants of order 2 in the numerator and denominator. And after some simplification, I am not going to do them. You can easily accomplish that. After some simplification, you will find out that this is simply A2, A3, B2, B3, C3, and C2 is equal to again A1, A2, B1, B2, and from here you are going to get A3, A1, B3, B1 into C3. You are going to get this. Is it okay? So maybe I can erase this so that it's easier for you. Okay, fine.
It will be A1 B B1 or A1 A2.
A1 where?
In the expression of C2 numerator.
Numerator. No, because I'm adjusting with the minus. I'm adjusting. See, I can take C3 out. I have taken C3 out.
Yeah.
Now, because I'm adjusting with minus, so that's why it has become
Second column. Second column.
A1. And
Second, yeah.
oh, this is sorry. This is B2. Sorry, this is B2, right? No, this is B1. Sorry. Yeah, now it is fine, right?
Yeah.
Yeah. Thank you. So now, if I look at C1 equal to this and C2 equal to this, from here again, I can get C1 by A2, A3, B2, B3. This is equal to C3 by A1, A2, B1, B2. And from here again, you can see that C3 by A1, A2, B1, B2. So that is going to be equal, simply equal to what? C2 by this. Okay. So basically, from these two, this relation and this relation, what I get. So C2 is A3, A1, B3, B1, and then C3 is A1, A2, B1, B2, right? And if I equate this into some non-zero scalar lambda, so that means what I can get, I simply get C to be equal to lambda, then your A2 B3 minus A3 B2 I plus A3 B1 A1 B3 J plus A1 B2 minus A2 B1 K. Is it okay? Fine?
Yes.
Yes. Fine. So now say I am saying that, and of course lambda is a real number, and I am taking lambda to be equal to non-zero, because if lambda is equal to 0, you end up with 0 vector, right? And then the orthogonality of that 0 vector with A and B, you cannot think about, isn't it? Right? So that is why I'm assuming lambda to be equal to non-zero. So obviously, you know that if lambda equal to 1 also, I can get a vector C defined by this, and I know that the vector C is going to be perpendicular to both A and B. Is it okay?
Yes.
Fine. So
Fine.
this vector defined in C is called the cross product or vector product of the two vectors A and B, and it is simply denoted by A cross. Okay. So now, because I have already expressed them in terms of determinant, you can easily see that this cross product or vector product of A and B, I can easily express them in this form: I, J, K, and then A1, A2, A3, B1, B2, B3. Is it okay? So basically, this is nothing but this. This is the part. Is it okay? Fine.
Yes.
So remember, that is the way the concept of vector cross product comes. Although probably you guys in your 11 and 12, you were told that okay, the cross product of two vectors A and B is another vector which is perpendicular to both A and B. Okay, so now that brings me to the concept of a right hand side system. Okay,
I have
so
a question. Can I ask?
pardon?
I have a question.
Yes, sure, go ahead.
So for applying Kramer's rule,
Uh-huh.
you have to assume that some determinant is non-zero.
Non-zero. Yes, yes. Determinant is non-zero. Yes, definitely. Yeah.
That
Yeah.
imposes some condition on A and B.
Condition on A and B.
This denominator determinant has to be non-zero.
Non-zero. Yeah, yeah. So this one, just a minute. This one, I have to assume that this is non-zero.
Yes.
See, one thing is that I have obtained it this way. But what you can do, you can simply eliminate, C1 between those two equations, and that is also going to eventually give you this expression. Okay, fine. And of course, if I want to do it through Kramer's rule, this tool has to be non-zero. This denominators. Yes, thank you. So now that brings me to the concept of the right-hand side system. Okay, fine. Why it is called the right-hand side system? See, if I consider my direction of this hand to be vector A and direction of my palm to be vector B and direction of my thumb, if I assume that my direction of my thumb is perpendicular to both the vectors A and B, so then I am having say, suppose they are almost looking like, yeah, suppose this is vector A, this is vector B. So since their cross product is going to be perpendicular to both A and B, so this pencil, it is along the direction of A cross B. Is it okay with everybody? Fine?
Yes.
Sir.
Okay. So now, if I tilt this, then you will see that now this becomes B, this becomes A. So if I take the cross product of B and A, so then I am going to get a vector which is perpendicular to both of them, but it is going to be in the direction opposite to the previous vector A cross B. Okay, fine. So that is why it is easier to infer that your A cross B and B cross A, they are going to have opposite directions. They are going to have opposite direction. And that is why in many book you will find out that A cross B, they write it is equal to minus B cross Okay, fine. So that means although your scalar product, dot product of two vectors, it was commutative, A dot B was equal to B dot A, but A cross B is not equal to B cross. Okay, fine. And again, here, if A and B, they are parallel, so then you know that B is going to be a scalar multiple of A, right? So then what is going to happen here? Here, instead of B1, B2, B3, I am simply going to get your lambda A1, lambda A2, lambda A3, right? And by the properties of determinant, if I take this lambda out, because then my two rows are going to be the same, so this is going to end up as the 0 vector. Is it okay?
Yes.
Fine. Okay.
Yes.
So that is why the cross product or the vector product of two parallel vectors, it is always 0. And remember that 0, this is 0 vector. This is 0 vector. So basically A cross B is equal to 0 if and only if A is parallel to B. Okay, so that is another interpretation. Fine. So now I will just discuss about a property on the side. I'll just quickly do one proof. Okay. The proof is there is one property. Is that your A cross B. So this is equal to sine theta, AB sine theta, where your theta is the angle between the vectors A and B. Okay, so now if I assume that this proof is pretty straightforward, I'm going to do it quick. See, if I take a B to be equal to B3, right? So then you know that your A cross B, this is simply given by A to B3. It is given like this. Okay? So that means if I consider the square of the magnitude of this, it is going to be A2B3, A3B2 whole square. So I'm not going to write it down, you know what it is. Okay, so then if you work this out, if you expand it and you do some kind of adjustment after simplification, let me guarantee you that this is going to give you, your this. Okay, eventually once you do this simplification from there, you are going to get. Okay, and if you look at this expression, then you can see that this is mod A squared, this is mod B squared, right? And this is simply what? A dot B, isn't it?
Yes, sir.
Right? And what is A dot B? This is simply mod of A, mod of B cos theta, isn't it? So from here, I am going to get mod of A squared, mod of B squared, cos squared theta. Okay? So from here you can easily manipulate it. You can easily take this out, then that is going to be 1 minus cos square theta, that is sin square theta. So eventually from there you are going to get this. Is it okay? Fine?
Yes.
Okay. So now again, see, these are all mathematical manipulation, algebraic manipulation, but exactly you should know how to visualize the cross product or vector product of two vectors. That is what I'm going to do. Just give me a sec. I'm just puffing off the last one. Okay. Say, suppose okay, suppose this is vector A, this is vector B, and suppose I am considering their cross product, then I know that it is a vector which is perpendicular to both of them. Suppose this is A cross B. Okay, so then you know that any vector P, it is nothing but magnitude of P into a unit vector along that. Okay, fine. So if I consider a unit vector n cap along A cross B, so then my A cross B, it is simply magnitude of A cross B into n cap. And you know that magnitude of A cross B is given by this. So I can write this as this. Is it okay? Fine?
Yes.
Okay? Fine? So now let us quickly go into that. So basically, the component of the cross product is given by this quantity. Okay, so geometric interpretation of cross product. Okay, fine. Say, suppose I consider this vector A, this vector B. This is A, this is B. Now let me complete the parallelogram. Let me complete the parallelogram. Okay, fine. So now, if this is H, so then you know that the area of this triangle, is half into this length into this height, right? So area of this parallelogram is simply going to be this length into this height. Is it okay? Fine. So
Yes.
area of course the parallelogram formed by the vectors A and B. Area of the parallelogram. So this is simply this length A into this height, and then you know that this H, if the angle between these vectors A and B is theta, H is simply your this, right? And this is nothing but this. We have already found out. Is it okay? Fine?
This is
Yes, sir.
sine theta.
This is sine theta. Everything is not okay. Because cos theta would have been simply this length. Isn't it? Fine? Okay? Thanks for correcting me. So, this is the geometric interpretation of vector cross product. Okay? So, now I will come to the concept of how much time do I have. Okay. Just scalar triple product. Scalar triple product. Okay. So, what is scalar triple product? So, I'm going to consider three vectors A, B, and C. Okay. And if their components are simply A1, A2, A3, B1, B2, B3, and C1, C2, C3, so then you know that your B cross C, it is simply B2, C3, B3, C2, B3, C1, B1, C3, and B1, B2, B2, C1. Fine? Okay? And then from the definition of dot product, your A dot B cross C, fine? It is going to be given by your A1 B2 C3 minus B3 C2 plus A2 B3 C1 minus B1 C3 plus A3 B1 C2 minus B2 C. Okay. Now, if you look at this, what is this? This is nothing but what? The determinant of A1, A2, A3, B1, B2, B3, and C1, C2, C3. Okay. So you know that these being the determinant where the entries are real number. Again, this is going to give you a real number, which is nothing but a scalar, right? So that is why this expression, it is always going to give you a scalar. And this expression is called the scalar triple product of the vectors A, B, and C. Okay? Fine? So now
Yes.
let us come to the geometric interpretation of this scalar product. Okay? So let us come to its geometric interpretation. Okay? So what is this? Okay. Say, suppose I consider these two vectors like this. Okay. Say, suppose this is B this is C. Okay, and suppose this is A. Suppose this is A. Okay, so then before going into what is going to happen to A, let me simply concentrate on. Simply concentrate on this parallelogram. Is it parallelogram? This parallelogram. Okay, so then you know that the area of this parallelogram is simply given by the magnitude of the
B cross C.
cross product of B and C. Okay, so now if I want to find out the parallelepiped whose edges are given by A, B, and C, so the volume of that parallelepiped, it is going to be simply given by, if you draw a perpendicular from the terminal point of A over the plane where B and C lies. So if this height is h, then what you are going to get, if this height is h, you are going to get simply h
Sine plus of B
this
cross C.
is going to give me the volume of the parallelogram. Okay, so now let us come to the cross product of B and C. You know that the cross product of B and C, it is a vector which is perpendicular to both B and C. Suppose this is it. Okay, fine. Suppose this is B cross C. Fine. Okay, and suppose a unit vector along B cross C is given by n cap. Okay, fine. So then if the angle between this B cross C and this vector A, suppose it is theta, so then this distance is what?
H.
H. So H is nothing but what? A cos theta, isn't it? A cos theta. Fine. Okay. So
Now it is obvious.
yes. So then what is going to happen? The volume V is simply H into B cross C, and H is nothing but your A cos theta. Fine. And if I accommodate this here, this, okay, and this is what? This is nothing but your A dot B cross C. Is it okay? Fine. So that means geometrically the scalar triple product of three vectors A, B, and C is nothing but the volume of the parallelepiped formed by formed by edges A, B, and C. That's it. Okay. So how much time do I have? I think I'm almost done. Just a minute. And in my slides, there are a couple of application of scalar triple product. Please go through that, because I have already spent 3 classes on the basics of this. Okay, I still have to do vector equation of a straight line in space. I think I have another 5 minutes, right?
Yes.
Yeah. So let me spend those 5 minutes in trying to find the vector equation of a straight line. And you will see that the concept of vectors, it is going to make three-dimensional geometry or solid geometry so easy to visualize. So let me do running out of chalks. Okay, anyway. Equation of a straight line in space. Okay, fine. So what we are going to do, say, let me consider the 3D space first. Okay, so now let us concentrate on the inputs. So what information we have? You have to find out, remember, these are the inputs. You have to find out the equation of a straight line in space which passes through a fixed point. Okay, that is the first information. So suppose that fixed point is say P naught. Its coordinates are given by x naught, y naught, z naught. And another information I have been given is that the straight line which passes through a fixed point P naught, it is such that it is parallel to a given vector. It is parallel to a given vector, say V. Given vector V. Is it okay? The information
Yes.
which we have, fine. So based on these two facts, we will try to find out the equation of the straight line. Equation of the straight line, say this is L's, this E elevation. Okay. So what I'm going to do, I'm going to take a variable point here on the straight line. This is P. I'm going to call it x, y, z. Okay, and then I'm going to join OP naught, and then OP. So they are going to give me one fixed vector, say R naught, which is nothing but OP naught, and a variable vector R, which is nothing but the vector OP. So far, so right? Okay. And now let us assume that this straight line, which is parallel to a fixed vector V, let us assume that the component of V are A, B, and C. Components of V are A, B, and C. Okay. So now from these triangles, you can see that R naught, or for that matter, your R is simply equal to R naught plus P naught P. Fine? OP.
Sir, video has stopped.
Now, can you?
Now it's fine.
It's fine. It is because of some internet connectivity. I hope recording is still on. Yeah. Okay. So now this OP, I'm designating it as R. OP naught is the shape factor R1. And now you can see that this vector P naught P, it is parallel to V. So P naught P, it must be some scalar multiple of V, where this D is a real number. Is it okay?
Fine, sir.
Fine. So this is P V. Okay. So if you want to break it down, what you can do, R is x, y, z. Okay. R naught is x naught, y naught, z naught, and V is A, B, C. So in fact, this is the vector equation of a straight line passing through the point P naught, whose position vector is R naught, and parallel to a vector V. Okay, I'll come back to this later on. Just I want to tell you one thing. See, if T is positive, if T is positive, so what is going to happen if T is positive? Then the direction of the vector dv is going to be along the direction of v. So I am always going to go like this and then this way. Is it okay? I am going to go this, firstly this, and then in this direction. But if t is negative, then the direction of P naught P is going to be in the opposite direction of V. So then what I am going to do? I am going to go in this direction and then I will move to this direction in order to find out the point P here. Is it clear to everybody?
Yes, sir.
Right? So that is why, I mean, if your T is greater than 0, this point P is going to lie on the right hand side of P naught. If T is strictly less than 0, it is going to lie on the left hand side of P naught. And if T is equal to 0, then what is going to happen?
P naught P is the zero vector.
That means I am simply considering the point P naught.
Yeah.
Okay, P is nothing but the point P naught. That's it. Okay, so I'll come back to this later on again in my next class, which I think is going to be next Monday.